Okay, let's start. Okay, first let's review last class. Last class, okay, we finished especially the DNS system. Okay, we know the DNS is the distributed database implemented in the application layer. And also for the DNS, okay, mute. Okay, for the DNS, there are three layers. Okay, from the root name DNS server to the TLD DNS server to the last the authority DNS server. So for user part, we can use the local DNS to query and for the different layers. Okay, and also the local DNS server also can use the can cache that mapping. Okay, from mapping, especially get the cache mapping of that the TLD the DNS servers. So finally, okay, if we get that because we know the DNS is to map from the host name to IP address, right? And there are two solutions to uh, query that the IP address from the authority DNS server. The first solution is iterative solutions. Second one is the recursive solutions. Another one is that we know for the DNS we use the resource record, okay, to do that query and reply message. For the resource record, there are four parameters. Especially in the third parameter, there is the tabs. Okay, so for the different tabs, for example, if tab equal tab field value equals A, that is the original purpose. So this time the name is the host name, value is IP address. And if tab is the another one AS, okay, that means we can map from the domain to the, the authoritative DNS server's name. Third one is that if that tab is the CNAME, that means we want to get the clock name. Okay, so this time name is the alias name, value is chronic name. Last one is that if that tab is the MX, that means we need to get the host name of the mail server. For example, if we have that especially the domain's name, and then we can use that MX, we can get the new server's the host name. We know based on these things, we for the DNS, we can get IP address, we can give a list name, we consider from domain to get the DNS name, and also from the domain name to get the new server's name. So last class I give an example, to show if we create a startup network utopia, and first one, we need to apply domains. For example, networkutopia.com from the register, like the network solutions. And also we give the primary and secondary, that is the DNS name and IP address. And also this register will insert that the two different resource record to the TLD server. For example, it will insert like from the first one is from the tab A. From that, the first one is tab NS. Okay, so that is from the domain to the DNS. Okay, the authority DNS server name. Second one is to tab A. So that will map from that DNS. Okay, the names. Okay, DNS1 networkutopia.com to that is the IP address. Okay, so that means for the TLD server, no, this company is the authority DNS server. Okay, finally, any user use the local DNS can find this authority DNS server. This authority DNS server at least to store that mapping. Okay, for example, for web server, for mail server, know that IP address. Okay, so this is just an example for here. We also discussed for the DNS, there are some, okay, the security, okay, issues. Okay, so it is challenge to attack the running DNS server because we can cache that the mapping in the TLD, so that okay lead to the second layer. The TLD server is more dangerous, and okay, for this case, we can say easy to use like the DDoS to attack that. Thirdly, someone consider to use the man in middle, we can intercept that DNS resource. And if we know the source and destination IP address, and then we can change the resource value. Okay, so previously they need to give IP address for that this company's web servers IP address, and we can direct to another web servers. Okay, that with the fake IP address. Okay, this class we mainly discussed about, okay, we quickly finish that peer-to-peer and also give an example for the BitTorrent. Another part is this class also we need to discuss that video streaming. If we still have time, I will discuss about the socket programming. First one is that, we need to review the client server and peer-to-peer architecture. For the client server, we know there is always on server. The server use the unique IP address, and the client can communicate with another client. And for the peer-to-peer, we can see each of the device can direct send data to another device. And also, there are no always on server. And each pair can bring that the capacity into these pairs, and also can request the service from other pairs. And the last class, I think we finished here. We discussed about we want to distribute one file to the n pairs, how much time to distribute this file. And we consider this upload rate is US, and each pair or each client and upload rate is the upload, that means from device to the network, and the download rate from the network to the device. And for this case, we can say each upload rate is from the U1, U2 to UN, and the downloading rate is from D1, D2 to DN. And if we choose the client server architecture, that means so each client need to get that file from these servers. So that means the server need to upload the n files sequentially into this network. And if we upload one file, that time is F over US. This is transmission time. And if we upload the n file, so the total time is NF over US. And then we consider if we plot this timeline here, this is T, this is there, this is there. And then we need to consider the server need to upload n times F over US. This time finally we can see this is NF over US. This time point, the server, sequentially, this is first, we consider this F over US, and this is 2F over US, 3, so this is another one is we need to consider the client need to download that file from the network to the server. So for example, the first one maybe download time is the shorter time in this point. We consider F over DI, and maybe someone is DA larger. Finally, that downloading time is longer. So maybe this time, if we consider this is D minimal, and then use the F over D minimal. So this is the longest time. So for the downloading. So finally, the time to distribute is F to the n clients. That using the client server architecture that equal larger or equal than maximal value. Is this value is larger or this value is larger? If for this case is if n is larger, become larger. So finally, this point. This point maybe become larger value. To move to here. And that means if n is larger, so the minimal distribution time depends on NF over US. So if we increase the number of users, so the distribution time also will increase, linearly increase. Second part is that if we consider use the peer-to-peer architecture, this time, okay, any peer can help to distribute this file. So that means if one server to download, okay, up to send that file to any one client or one that is the peers, then this peer also can upload this file to the other peers. So that means one peer joining this network can request that file, also can provide that service into this network. And for this case, we can say server just upload one file into this network with the time is F over US. And each client also download that time. Also similarly, we just consider the slowest time, maximum time that equals F over the minimum. So finally, okay, we can say there are two terms. One is F over US, another one is F over the minimum. Another case is that we need to distribute n files to n pairs. So aggregation time that equal use the total file nf over the aggregation capacity US plus the sum ui I from 1 to the n. And for this case, also we interesting the largest value is this one, this n. If n is become larger, and okay, we can say this part, that capacity, the aggregate, the capacity also okay increase. So finally, we can say that will become the constant value or in the same level values. And if we plot the client server and peer-to-peer, we can see like this figure. And if we increase the n for the client server architecture, so we can see minimal distribution time also linear increase. Okay, so if n is larger, and that the distribution time is larger. And if we consider the peer-to-peer architecture, and for this case, if we increase n, for example, from 20 to 30, that increment so for that time, that is very small, just increase that 0.1. And if you check out that the distribution time with the client server architecture, that we can see from the 2 to become 3. Okay, this is increase with the 2 point, and this is just 0. Okay, 0.1. So for this case, that means if we continue to increasing that number of users, and to distribute that file, that minimal distribution time for the peer-to-peer, that keep or maintain in the same time. But for the client server, we can say that is the increase larger value. So for this case, that means peer-to-peer, we can use this architecture to support some file distribution. Okay, because even though for the larger network and that the minimal distribution time also that is maintained in the same level. Okay, based on this architecture, we can discuss this, BitTorrent, this app. For this one, idea is that, we just to discuss the core that is the algorithm or ideas. And the first one, if we want to distribute that file, so we need to consider to divide that file into the several multiple chunks. For example, 256 KB for each of chunks. And in this, the torrent. Okay, what is torrent? Torrent is group of the pair to exchange that chunk of the file. And pairs in the torrent can receive or to send that file chunks. Another way is that for this BitTorrent, it needs a tracker, to keep track that the pairs that are participating in the torrent. And for this scenario, if we suppose that one user like Alice joins this BitTorrent, first, I need from the tracker to get a list of that pairs, and then just to connect the subset from the list. For example, like this case, we connect 3 of the device. Another way is let's check out the basic idea in the BitTorrent. First way is that if Alice joins this BitTorrent, in the beginning there are no chunk for her, and over time, so the Alice can request that chunks from the 3 pairs to accumulate that chunks. Okay, and another feature is that let's just connect the subset of this pair from the list of the pair. And Alice also can download the chunks from the neighbor pairs. At the same time, also can upload chunks to other pairs. So peer-to-peer architecture, we can send data, we also can receive data. Another case is that the Alice, in this time period, just connect this 3 devices. In another time period, it can connect other, the pairs to exchange chunks. And so another feature is that, if Alice received the 2-to-fire, so she may leave or just remain in this torrent, to contribution this file sharing. And there is a question, here. So Alice joins this torrent, how to request the chunks, how to send a chunk. So what's the strategy for these 2 things, sending and receiving? First one is we consider how to request chunks. If we need to request chunk, we need to consider, for any given time, that the Alice can connect the different, that the pairs. And from that pairs, the subset of these pairs, and Alice need to use strategy called rarest first. The solution is rarest first. What's the rarest first? I give an example. This is Alice device. There are the different pairs in this torrent. For example, we consider there are 5. And Alice just connect subset. For example, that just connect the first 3, that pairs. And each of these pair have that different number of chunks. For example, if we divide the file into the 1 to 6 chunks, and the pair 1 have the 1 to maybe 5, and pair 2 have the 1 for 5, and pair 3 have 1 that for maybe 6. And for this case, Alice need to request that the missing chunks from the neighbors, these connect pairs, using rarest first the solutions. So rarest first that we just count the number of the repeat number of the repeat chunks. So this is the 3, 1, and 2, 5, 2, 4. So just 2 and 6 just appear 1 times. So for this case, that Alice just request 2 and 6 first. So we call this is rarest first. Another way is that this is how to request which chunks from the pairs. Second one is that we consider how to send that chunks to other pairs. This solution is how to send that use the tit for tat. The idea is that Alice connect the for example that 4 pairs. And how to connect that 4 pairs, Alice check out, evaluate that sending rate. So first one, Alice send data and also Alice receive data. And check out the sending rate, to choose the top 4 that pairs. So for example, this sending to the Alice with the rate is R1, R2, R3, R4, R5. So that is to rank this to choose the top 4. And Alice just send the top 4 pairs. And other, for example, last one just will not receive the data from Alice. Another way is every 10 seconds, Alice need to re-evaluate top 4 pairs. Another stage is that every 30 seconds, and Alice need to randomly choose another pairs, because maybe even though this pairs to send it more data to Alice, and but there's still issues if this pair doesn't have that the remaining that chunks. Alice also still will not get the 2-2 pair. The solution is we also need to randomly choose another pair, and Alice need to start to send in chunks to see the feedback. If this pair also send data to Alice, then that need to become the new top 4. This is solution for the T4 TAT. So we can see Alice here, and every 30 seconds, Alice need to randomly to choose one pair, like Bob, and send data to Bob. And this time, because Alice sent more data to Bob, so Alice may become the top 4 that pairs, for the Bob. So become one of the top 4 providers for the Bob. And then check the Bob's feedback. If Bob also send data to Alice, then Bob also becomes the one of the Alice top 4 provider. And then we can remove like one the low data rate from this group. And Bob also remove one low data rate from Bob's group. We can say we call this one is if we want to get that the data that chunks. First one is we need to use the hair upload rate to sending data to that one pairs and check all that feedback. So it is easy to find the better trading partner to create that pairs. So after this one, we can see it can distribute that pair quickly or faster. So why we then let's check that features. Let's back use this slides. First feature is request chunks. That use that the neighboring pairs to using the rarest first to request to request missing chunks. What's the why? The idea is that Alice want to redistribute that the rarest chunks to the others in the future. So finally we can equalize all that the chunks in the different pairs. And the second one is that use the T for TAD to send that chunks because I want to find the better the trading partner to find out the expected that the chunks. So this is the two important mechanism in the BitTorrent for the peer-to-peer. So here is we can see we finish the peer-to-peer. I introduce the BitTorrent, and you need to know how to request chunk, how to send chunk, what's the solutions, the different solutions. And this class also we need to mainly discuss about video streaming and a content distribution network. And the first one is that why we need to consider video streaming. So if we consider that the current video streaming, that data, this traffic, this is become we can say like the Netflix, YouTube, and Amazon Prime. So this is used 80% of the current ISP the traffic. Special at night, and so this is large data for the internet. We need to handle some issues. For example, how to schedule, how to get that video, from to support billions of the users for scalability problem. This case is that how to scale, how to reach that 1 billion users. And for this case is that we need also handle like the heterogeneity that issue for the user. For example, different user have the different bandwidths. Like for our this Zoom meeting, we can say the different student maybe have the different internet service. And for this case, how to to send that video for the different users. who has that different capacity to connect that internet. And based on this issue, we also need to propose like the distributed, the application layer structure. We call that is the content distribution network. And before this one, we need to first discuss. We discussed the video streaming. So what's the video? This is the basic element for this protocol. For the video, that first we know, plays video. We know this is the sequence of the image, with the constant rate for the display. And for example, we consider 1 second 24 image to play that videos. And another one is we know this is video, and what is the digital image? And for each image, this is array of the pixels. So that means each pixel we can use the digital bits to represent that. Another way is that if we transmit video, so video is the higher data set. We need to use the redundancy in that image or the between sequence image to decrease that number of the bits. Decrease that data set. So we consider this is the encoding, coding part, video coding. And the solution is like, first one you consider spatial coding. And for the one image, this image, we can say previously we need to send the total image. Each of we need to send total pixels. And that means we need to use the more data, more bits to represent this image. So how to reduce that data? The solution is that we can use that color value and the number of repeat value. If this is the similar, this area, most ever, this part, just the same, that values, color values. So we just transmit, this color value and the number of the repeat values for these solutions. And the second solution is we want to decrease that number of bits. We can compare the frame I and the frame I plus 1. And for the frame I plus 1, and we can say if we compare these two images, it's easy to find most of part, this area on this image are same. And we just calculate that the difference between these two images. And then we just send the first image, and then we complete that the second image with that the difference value. Or for example, we send frame I, then we can send that the difference value. And if different value is sparse matrix, or this is just a small number of value, then we just use the difference plus the frame I. We can recover the frame I plus 1. So there are different solutions for the coding, the special coding of this video part. And there are different standards that use the CBR, the constant bit rate, or the variable bit rate. And for the standard like the MPEG-1 to MPEG-4, and like MPEG-1 to support the CD-ROM, and with smaller bit rate. And MPEG-4, we can say that is considered for the internet, that is for the up to 12 Mbps. So previously we discussed the video. Then currently let's focus on our internet protocol for the special for the video streaming protocol. For this protocol, we can say first one we need to consider use the which architecture. Use the TCP or UDP. The first one for the video streaming, then consider the client server. There is a client part, there is server part. That way is it used for this case use the TCP. And so here there is video server. That means this server to store that videos. Different video like movies or other videos. And then the client use like the player to display that videos, right? We can watch the YouTube or Netflix or other video streaming. And for that case, we need to request that videos from the video server to our client part. And what's the challenge to request the video? So video streaming, we need to consider like the real-time video display playing, and this is not like the web, to request the web page, or not like that email. So because web maybe that is the longer time or to get some other object, but for this case, we need to get the smooth video streaming. So what's the challenge part? Challenge here is that you need to use internet network code to get that video, and that from the client to server, this throughput, end-to-end throughput or bandwidth will change, over time. Sometimes that internet there is no connection, the internet speed is higher. Sometimes the internet speed is small. So for this case is that if we propose that protocol, how to handle these congestion levels, in the different scenarios. Second one is that, we know if we use the TCP and because of congestion, there is some packet loss or queue delay. It will lead to some buffering, rebuffering, or delay some playout, and finally generate that poor video quality at the client part. So there's still some challenge for the regarding the bandwidth part or the client part. Let's see this example. First one is that we need to consider to get that video, and there is the video server here, and this video server can record that the video, for example, with 30 frames per second, to get. This is cumulative data over time. Trunk 1, trunk 2, trunk 1, 2 trunk, 3 trunk. So finally, we need to consider this similar things with BitTorrent. We need to divide it, that the video to different trunks, a smaller video. For example, if there are 1 hour videos, we can separate each trunk with maybe 2 seconds. So like this. And then, server, if client requests that video trunks, the server can send that video. And from here, this is the recording. So that is send that video over, this first trunk, second trunk. And there is the delay, right? Network end-to-end delay. And for this delay, at the receiver, for the client part, we can receive that video trunk to get, for example, here. Get the first this is the first trunk arrival here, and we get the total first trunk in this time, second trunk in this time, third trunk in this time. The client also can play, for example, streaming this at this time. The client play out that earlier part of video. If we receive that video, trunks, we can play that. And the server at the same time, and you can see here, this area also continue to send that data. And this is to play. So we can see, we can smooth this line. We can, each of this part we receive here. And also it get the new trunks. This is like the good for the video streaming. But if we consider real case for the internet, so there lead to some issues. Let's see. First one is that, let's check some issues. If we continue play out, that video, and during that video play out, we can see there are some, the play out time need to match the original time. And for this case, because the network, that bandwidth or throughput is variable, will change over the time. So for this case, that buffer needs the client, that buffer need to match that the continuous play out that constraint. And for this case is that if that there are no data for the client buffer, so there is to appear buffering. So that means the client need to wait that video chunk from the video servers. And also we need to handle other cases like if we fast forward. Okay, so there are no data from the servers. Or we to post or rewind or jump from that videos. Another case is that for the challenge is that if some packet lost, we need to retransmit that. Okay, a lot of issue we need to address. And let's check that figure, the same figures. And if the client requests that videos, and the server for this red curve, that is show the setting that the video chunks. And for this case, this is real, okay, from over the internet, the chunk arrivals that this client with the different delay. Okay, this one, let's see. This use this time arrive here. But the second chunk arrive here is longer time. Okay, interval. And the third one is smaller. Okay. So there we can say the different time to arrive at the client. We can say this network delay is variable. And then we need to see, okay, what's the time, okay, to play out that video. Okay, for example, if like choose this time, if we play that, okay, so that means currently this client have this trunk, all these trunk 1, trunk 2, trunk 3, trunk 4, trunk 5. We can play this. And also if we play this with the constant bit rate, and then, okay, we can see for this case is that there is like no issues from here. We can continue also to get that the videos. And okay, based on these things, we can see that we can use that, like especially we can consider the buffering and play or delay here to address that network added delay and delay, okay, jitter. Okay, so let's check out if what's the basic one if we want to okay request that video chunks. Okay, I show here. And for the this is server, this is client. Okay, that use the internet to get that video chunks. And for the client part, there is we know there is the buffer. Okay, to show their buffer here, buffer size here. And this internet, that throughput. Okay, we can say that is this is the variable over the time. And we consider if that throughput is larger, that means more data will arrive at this buffer. Okay, and this is buffer part. There have two stones that chunks. Another way is that here this is the play rate. Okay, and this is to show show that video. And with the we can say this is we used R. Okay. And this is used this is the used capital R. This is the lowercase r. Okay, if we consider that if R is here is okay, if the data rate is larger, right? Okay, so that means more data arrival here. Okay, and for this case, okay, we can say there are no rebuffering issues, but one issue is that maybe that overflow for that buffer. Okay, next time this client to request that video chunk, they need to consider the higher bit rate or lower bit rate. Okay, so in order to address this one, and let's check out very important industry standard for the video streaming called DASH. Okay, full name is Dynamic Adaptive Streaming over HTTP. So if that use HTTP, that means it on top of the TCP and the client server architecture. And so this is client. We can request the video chunks from the different servers. And for the server part, it needs to divide the video file into the multiple chunks. Okay, this is similar with that the file distribution, because each chunk maybe we have the video. Okay, we have video. For example, the 10 minutes video, and for the third parties, we can separate that video into the different video chunks. So each video chunks maybe we have considered 2 seconds. Okay, like this one. And another thing is that each chunk is encoded at different okay, the data rate. Okay, that means some chunk, okay, with the higher data rate and some chunk with smaller data rate. Okay, and this data, okay, different data rate is stored in a different file. Okay, and the last one is that this file is replicated in the CDN nodes in the different nodes. And also we need to give the URL because if we consider HTTP and we use GET, okay, second one is URL, okay, HTTP versions. We need to use the URL to find this video servers. This is for server part. That means for this case is that if we have that video, then we have a different copy of that video in the different servers. Another case is also for the video we divided that video into the the video chunks. Also, we have the different copy of these different revolutions for each of the device. Okay, for example, we have the from the lower revolution to the higher revolution in this part. Okay, and okay, for this case is that if internet, let's check the client part. Okay, the client need to estimate the end-to-end throughput or bandwidth, and then request that chunk at one time, and using manifest file, use the URL, and how to choose the video chunks. Okay, given that current throughput, we need to choose the maximal coding rate. For example, if that the bandwidth is the larger, so we need to choose the higher that data rate. If the bandwidth is smaller, we choose the lower that bit rate or data rate. And also we can consider to choose the different data rate at a different time point. Okay, so because the bandwidth will change over time. Okay, and also maybe we can choose that video with the different video server. Okay, so if this server that congest require longer time, and we can choose that data with another video servers. Okay, so if you check the client part, so this is kind of like the most smart intelligence. Okay, because this is protocol called a dynamic adaptive streaming. Let's check the client part is that the client need to determine when to request the trunk. Okay, and for this case, that the client need to check out that information here, the buffer information, and here is we can see this is the way this is throughput. Okay, this is we consider the T, and then we need to consider for the data rate, the different data rate we consider R, and the pre-auto rate is the little r. And for this reason is that if this is network is good, is larger if we place that the video with the constant rate, for example, that is 20 frames per second. And if the R become larger, and that means more and more chunks arrive at the client buffer. Okay, and for this case, that means we just get the lower bit rate, and finally the buffer just with limited size, maybe overflow. And for this case, we can request higher bit rate. That is the code rate, encoding rate. So if we consider higher coding rate, you need to know that each of trunk. And there are 2 seconds. If this is the higher bit rate, that means that is the larger data. We use that times that data rate, the R. So this is the packet length, and then we use this one to over that the throughput. So we can over the throughput, we can get that the current translation delay. it, if this is larger, this delay current that is smaller, okay, faster arrival to the client part. So for this time, okay, client okay make that more smart to choose the higher R, right, higher bit rate. If network become bad, okay, smaller value. So this time the client can choose the lower okay bit rate, okay, for the lower smaller okay encoding rate. And also that is consider okay, so check out that buffer. So if buffer is starvation, okay, so that it gets that. If overflow, just okay for this case, okay, maybe wait for to request that video chunks. Another one is what encoding rate to request. Okay, this depends on that link capacity, link bandwidth. Okay, the higher bandwidth we consider higher quality, high quality of that data. That means the higher encoding rate. Another way is that where to require chunk. And for these cases, there are different servers. Okay, traditionally we can use to choose one server close this client. Okay, because this is with the smaller propagation delay. Okay, and if this also this server, for example, if this the close that client, and if this router is congest, and then this time the client can request from other servers. Okay, so and with the small okay list end-to-end delay. So finally, we can say video streaming is equal encoding. For the video, we use the different encoding rate to represent that video. Second one is that consider protocol is the dash, the dynamic adaptive streaming over HTTP, and also consider play out buffering. Okay, so previous we can delay that to play out that video. So this is first case we can say we just consider end-to-end, one node to another node. And another one is let's check out like this content distribution network. For content distribution network, okay, for this case, the challenge part is that we need to consider how to stream the content. Okay, so for example, millions of videos to okay, also the maybe the millions of that simultaneously users. How to scale to the larger network? The solution is that if we consider one, okay, the video service. Also, this is similar things like the previous, the DNS, right? There are similar issues. Single point failure or contract issues, long delays. So why we need to choose distributed? Because if we consider centralized solutions like the mega servers, so it doesn't scale, okay, for this solution. Second solution is we consider to store or serve with the multiple copy of video at the different, okay, the geographically the distributed the video servers. We call this one is the content distribution network. We can okay to store that video in a different different place with the different video servers. And there are two solutions to deploy that video servers. One is interdeep. Okay, interdeep idea is that we can deploy more video servers in the access network. Okay, so that is near user, close users like the Acmail. So this to deploy that 240,000 of the video servers in the world. Another case is that we can consider the bring home. Okay, so this solution is that we need to deploy the some larger cluster number, small number of larger cluster in near that access node in the POP that exchange nodes, the higher that is the layer. And for this case, bring home that means and this is a longer delay and it can reduce the cost. Okay, so that just consider some cluster in here. And let's check all that content distribution network. And for example, Netflix can store that copy of that video into the different CDN nodes. Okay, this video server. We can see if we use that the interdeep. So we need to deploy that video servers in that access network. Okay, we can say the different access ISP. Okay, that in the different area, geometric the area. And then if we see if one client want to watch that movie, and then he first to contact that video server. Okay, the subscriber requests that content. The server need to give that the manifest file URL. Based on that manifest, that know for this movie, where we can find that movie. We use that the URL. Okay, and then based on the manifest, that need to choose the one that the video server, for example, the closest user, right? And with also maybe that is hair throughput, we can retrieve that content. And if this path is become congested, and also that this client also can choose another path, another the video server to request this. Okay, so this case we can give the more choice for this client to download that video. Okay, to connect this. This is because this is content distribution network. Why? If you use Netflix, so we can get a very high, like 4K or 1080 that resolution video stream. Okay, if we consider over the top, and if we see this is internet to provide end-to-end communication as a service, and we need to adjust that congestion, the internet from the edge part. Okay, so we need to consider what content to place which CDN node. We need to deploy this node or another node, and also we need to consider from which node to get data. Okay, so based on the congestion level, and what is the bit rate we need to get? This is depends. We use the dash. Okay, depends on the current throughput or bandwidth. If throughput is the higher, we get the higher bit rate. Throughput is the lower, we get the lower bit rate. Okay, this is the solution. Okay, another way is that let's hear this new slides. Okay, remove this part. Okay, quickly introduce. Okay, end of slides. So for example, how to get one video server, how to connect video servers. And for this case, if we both request that the video from this net cinema, this web server, how to do that? We need to combine our DNS knowledge to do that. First, we know this company just use the content distribution network to deploy that video in another server, not in the local. This company is a video server. Use another third party to store that video. So finally, the video is stored here. Okay, and how to connect these servers? Okay, first step is that the Bob need to get the URL for that video servers. Okay, for these servers, and for this case, that Bob need to visit the web server. Okay, so this one, and in order to visit this one, I think you need to review the previous knowledge. We need to consider, for example, first need to get the IP address for this, right? And how to get this one? And we use DNS finally get IP address here. And the second way is that for this, netcinema.com for this the URL, and we use that Bob local DNS server to contact with this company's the DNS authority DNS. This DNS, another purpose is that gives that another information. If we consider to use the CNAME, so CNAME is that we can consider if we tap that that one the LSA name, we can get the true name, canonical name for that that servers, special the third party DNS servers here. And after this one, the Bob local DNS server can use this solution to find that CAN CDN authority DNS server. If we know that this IP and this host name, then that will to the step 4 to give information for the client, okay, to return that IP address for this video server. And then this Bob get that the IP address for this. Then we just use HTTP with the dash standard to request that videos. Okay, this solution. Another one is that for Netflix the case, and that use the third party like the Amazon Cloud to deploy that video in the different CDN servers here. Okay, upload that different copy, multiple versions videos into the CDN servers, and then if user want to request that videos, how to do that, and based on that the account, and that will can know the information for the Amazon's that servers. And the Amazon the cloud will return that manifest file. Okay, this file give that URLs for the different video servers, CDN servers. Then that Bob just to connect with the closed the server, one servers. You over the dashboard, we can request that videos. This is a solution we can see. So why we traditionally use the CDN? So we use CDN to deploy that video servers in a different area. Okay, and for the different area, different access network, then client to request that video, we give them multiple choice. Okay, to give that video with the lowest, the less congestion, network congestion. Okay, so in less network congestion, that means this data or this network current with the higher data rate to that client. Okay, so this is a solution. So like Netflix also use the dash and CDN, okay, for the video streaming. Okay, here I think we finish that video streaming. Let's summarize here in this part. Okay, first one is for the video streaming. We discuss what is the so discuss what's the video, right? And so we need to consider that is sequence of the image, and also we want to decrease the data rate. We need to use encoding. Okay, so from spatial and temporary encoding, the MPEG 1 to MPEG 4 for the different encoding rate. And the second one is for the video streaming. There is the video server. There is client. The client need to request the video from that video server, for example, over HTTP protocols. And for this case is that, so the issue for here, there are different users, and that user with different internet service. Another case is that the bandwidth end-to-end throughput will change over time. For this case, we proposed, because if request that video, and finally that video trunk arrivals at the client part with the different delay. Okay, we use like the pre-all delay. Okay, and so we proposed on top of this, we proposed a dash protocol. Okay, dynamic adaptive streaming over HTTP. That means for the third part, we need to divide that video into the different chunks. And each chunk is encoded with different bit rate. And also there are different versions for that bit rate. We consider to deploy to store that video in the different CDN nodes. And also that the server like the Amazon Cloud has that the manifest file. This one provide for the video with the URL. Okay, so we based on if client get a URL, then we can connect for the different video, or for example, close the video servers to request that. And the client part, how to get that, to evaluate bandwidth or end-to-end throughput. If throughput is here, we can request higher bit rate. Throughput is lower, we request the lower bit rate. Okay, also we consider when to request that. Okay, if that buffer, there are buffer for the client. If buffer is division, so we need to consider to request, maybe smaller, that bit rate. First, that means we need to light that trunk as fast as possible to arrive at these buffers. And if that overflow, we need to consider higher bit rate. Okay, so a longer time arrive with this buffer. Okay, this is solution. That means client part is smart. Okay. And last semester also, I think I introduced more knowledge in this video streaming. Okay, so for the client part, So current solution is that we can make that more and more smart. We can use AI. Okay, we can make decision based on some feedback, network feedback, like throughput, delay, and the client to use the neural network to make decision to request the higher bit rate, lower bit rate. We want to improve the quality of the user experience. Okay, so that means we need to guarantee most of the time we can get the higher data rate, higher resolution to play that video. Okay, another part is content diffusion network. There are two solutions. One is interdeep, another one is the bring home. Interdeep is to deploy that video server in the access network, which is closer like user. Okay, bring home, that is we need to deploy the small number of the cluster to store that videos. Okay, the longer delay but reduce the cost. Okay, another solution is that we need to consider for the content distribution network, and we need to store that video in a different video set, right? So finally, like that Netflix example, and we use that third party to deploy that videos. And if we know the manifest file, we can connect one video service. Okay, I think here let's tackle that this roadmap for this chapter. We first discussed the principal network, and we discussed client-server architecture and peer-to-peer architecture. We discussed the process. We discussed about the socket, and we discussed about like the service model, like the TCP and UDP. And after this one, we discussed we can say 5 apps, 5 different protocols. We discussed HTTP, and for the web, SMTP and IMAP. For the email, DNS to transfer from the hostname to IP address, or give the listening name, or from domain to that the authoritative DNS server's name, or from the domain to give that mail server's name. And also we discussed about like the P2P. We discussed BitTorrent, how to request that file, how to send that file. The request we use the rarest first. How to send we can use tit for tat. Okay, last one, this class also we discussed about video streaming. Okay, so special we discussed the Dash. For the Dash protocol, we need to consider, okay, so for the server part, for the client part, how to do that. Make that smart for the client. And we depends on that bandwidth, we can request the higher bit rate or lower bit rate. Depends on our buffer size or depends on the current throughput. Okay, and also we use the content diffusion network to increase number of that to support a larger number of the users regarding the scalability problem. Okay, so we finish all the application. I'll quickly summarize that. So last time, let's introduce the last topic in this chapter. Okay, so this chapter we need to discuss about the socket. Okay, earlier I think I introduced the socket. Socket is the interface connect application layer process and transfer layer this architecture. So this part, previously we just give an idea. There is client socket, there is server socket, and this part, this class and the next class, and let's need to discuss about how to write the socket for the client server. And this socket also need to choose the different, can choose the TCP or choose the UDP. So we can say socket very important for the developer. We just, for example, on top of this internet architecture, and how to send data, we need to use socket. We use socket to send data, from the application layer process to the transfer layer. And transfer layer get the data to create the segment, then go to network layer to get a datagram, to the link layer to get a frame. We know in the transfer layer, there are just 2 service models. One is UDP, another one is TCP. UDP provide unreliable data transfer. This is simple, faster. We know current the HTTP version 3 on top of UDP, right? And DNS on top of UDP. And also like the
DHCP on top of UDP, ARP on top of UDP, and some audio video streaming on top of UDP. So UDP also is very important, okay, that transport layer service model. But in this chapter, most of that protocol we discussed with that TCP, like from HTTP, SMTP, or like to the dash, or like okay, so many of us use the TCP protocol. So this one provide reliable, okay, bad streaming oriented data streaming, the data transmission. And this is TCP need to handle the flow control, contact control. There is 3-way handshaking for the TCP. Okay, and we know that two features. And this class, okay, I give that example. So how to use the socket to implement some app. And this is just an example to show if one client to read long characters data from its keyboard and also send that data to the server. Server's purpose is to convert that character to the up from the lowercase to the uppercase to the capital. And case. So third one is that the server okay need to okay send modify the data to the client. And so finally the client receive that data to display that data on the screen. In the real world, there are so many okay that network app on top of this socket. Okay, so I also have some project, for example, for localization, sensing. I need to deploy the servers. And if we want to run some AI models on our server, so if we collect data from the smartphone, we need to okay, upload this data to the server. And the server process that data, for example, estimate location or estimate that gesture, okay, to recognize gesture, and then give feedback, okay, this is location in this position. So give feedback to the user. So this case also we need to use that as a socket for the transmission. Okay, if we know this example, very simple, we just okay send lowercase, okay, that is the string of the character to the server. Server transfer to the uppercase, and then to send the modified data to the client. Finally, we receive that and display this data. And the first one is if we use let's check there are two different architecture in the transport. If we consider UDP, this is simple. Okay, there are no connection between client and server. Okay, so just send data. Okay, as fast as possible. And also for this case, okay, sender need to attach that the destinations, okay, the IP address and the port number to issue that packet. And receiver get that the IP address and port number from the receive the packet, and then to okay no to receive that data. And UDP also issue is that maybe the lost for the packet. Also maybe order for that packet. So for these issues. Okay, and generally we know UDP provide unreliable transfer of group of that the bits. We call this a data graph. And how to write the code? This class there no enough time. Let's first check out the basic interactions. So there is server part. We know UDP for this case we just discussed the client server architecture. So server is always on. We need to run that that server socket on that okay this device. And the first one that means we need to create the server socket. How to create that? That use this okay function socket. There are two parameters. First parameter is EF, the INET internet. And for this case, that means we need to choose the IPv4. Okay, this is v4. Okay, with the 32 bits for the IP address. The second one is if we consider same parameter is the okay socket, so that the datagram. Okay, if we choose this one, that means we choose the socket. Okay, this is application layer. This is transfer layer. This is socket. Okay, if this use the socket to create the server, second parameter is the socket datagram. That means we need to choose the UDP. Okay, transfer layer service model. And this is server part. And the client part also use the same function, the socket, to create the client socket. Okay, here, this one. And then if we create a client socket, and then we just need to know what's the destination's IP address, server's IP address, and for the server, this port number. Okay, we need to send the datagram by this client socket. And we know that information, we can send data to connect that server. Okay, create to connect that server. And the server read that datagram from the server socket, create server socket. And then we can do the basic operation, for example, to transfer that from the lowercase to the capital case. And then to reply the modify that line of the characters to the client. Can read that modified data and then display this, close that. This is the two-step. Okay, let's check. Okay, first one we have. Let's check this. So why we use the Python to write source code? Because for the UDP part, we can say there are just about the 10 lines to finish this. Okay, that is that code. First one is we need to the import that the socket class, and then we need to consider what's the server's IP. Okay, also give it a host name or give it IP address for the server. And another one is we need set that server. Okay, what's these applications? What's the port number? And for example, and also if you want to set up your servers, and then you also give the one this application's port number, and then the client need to create the client socket and with IPv4 and UDP to create this, and then we come from the keyboard to get data. Get a message. Lowercase message. And another thing is that currently when you use that client socket, this object, call function is sent to send that data. Here is this message. Because UDP and TCP just support byte streaming. Okay, so here is we need to encode that is from the string to the bytes, called the encoder function. And also attach that the server's the IP address or host name and the server's that port number. So then this data will transfer to the server. Okay, and then that client just wait for the response information. And that use another function is receive from. This is buffer size to receive that data, modify data, and server's address. And for that data, this is also bytes. We need to decode that to transfer to the string. Finally, we can print that data. Okay, so we need to close this client. Okay, and another part is for the server. Server need to also get import that server socket, and another case is we need to welcome with this corresponding port number, 12,000, and create server socket with same IPv4 and UDP. Source datagram, and we need to band that port number with this socket. Okay, so maybe there are different sockets, but for this time, for this proper function that corresponding with this port number. Okay, we know the port number is regarding that the specific process. And here we can see server is ready. This is always on. That means this is forever loop, true loop. And the server just use receive from to get the data for the message and get the client address. And then that is do the basic operation to decode that to transfer from lowercase to uppercase. And then we need to send reply that data, use encode that from the string to the bytes and attach that client address to send this one. We finish. This is server. Okay, so this one is simple for the UDP server. Okay, let's stop here, and the next class on Thursday we can finish this chapter. We need to discuss the TCP, and also I will review that again, give an example how to implement that socket for the UDP and the TCP. Okay, let's finish here. Okay, see you next class. Okay, bye bye.